Welcome to this lecture. In this lecture, we will talk about chapter 5, that is the development and evaluation of process flowsheet. Chapter 5 brings things together to look at the reaction, separation, and recycle elements of the flowsheet. And this chapter will look at the synthesis of these flowsheets. So here are the learning outcomes for this chapter. We will look at considerations, issues, heuristics, and performance, and how to maximize the performance of a particular process. Section 1 looks at the issues related to reaction, separation, recycle processes. I note here that we are only looking at continuous processes in this chapter. Similar issues are relevant for batch processes, but there are some extra considerations around scheduling. And these are covered in part in batch processing course unit and in addition in Robin Smith's book. So if you want to have a look at it in more detail, please have a look at these resources. But these are not covered here. They are out of the scope of this unit. In synthesizing recycle, we start at high level with little detail and gradually add detail and iteratively evaluate the flow sheet as it increases in detail and as the design decisions change. Back in chapter 1, we looked at the idea of input-output structure, and this very basic structure with almost no detail considers only what reactants and other materials are entering the process and what is coming out of the process. In chapter 1, we also looked at reaction separation recycle structure of the flow sheet in very brief detail. And the next step now is to look at the detailed configuration of the flow sheet. And even with reaction separation recycle structure in place, we still haven't defined what technologies we are going to use. And for example, what kind of reactor we are going to have, what kind of separation we are going to have, if there are phases involved in the process, and what would be the unit operations and what would be the conditions in each of this unit. And here I provocatively ask the question, is there a recipe for this? And I hope by now you will immediately respond no, because there is no simple step-by-step process for developing optimal flow sheet. And here lies the challenge and the satisfaction of process synthesis, because there is no one solution and we have to look at all the possible solutions and then develop approaches to choose the best possible solution. In order to evaluate whether the proposed flowsheet meets our needs and satisfy the constraints, we need quantitative information. So we draw on our chemical engineering techniques of carrying out material balances and energy balances. Knowing the flows of material and energy helps us understand some aspects of the flowsheet performance. In addition to material and energy balances, we need to evaluate the capital investment and other economic variables of the process. And this in turn requires us to design the equipment so that it can be costed. As we discussed in chapter 1, process economics is not the only aspect of the process that is relevant. The plant also needs to be environmentally friendly and safer to operate. This slide outlines key questions for deciding on the flowsheet structure. In particular, do we need a recycle, a purge, and how these impact on the performance? Furthermore, even a flowsheet that works may not be the best flowsheet, and we need to identify a good solution, not just a feasible solution. And what is a good or best solution? So defining this is the part of process synthesis, and it depends on the context of the economics of the process, its safety, its operability, and environment. In previous chapters, we talked about that recycles are useful in chemical processing flow sheets, but now we look at the need for process recycle. And as you no doubt know, that it is challenging and expensive to achieve very high conversions in a chemical reactor. and complete conversions may require an indefinite large resistance time, that is a large reactor. And in equilibrium limited reactions, you still might not be able to achieve 100% conversion. Increasing conversion may also promote competing reactions or side reactions, and as such, you might reduce your yield. But the raw material and the waste associated with unreacted raw material due to low conversion is also another expense. Okay, so note that while the waste can be a problem, many undesired byproducts do have a value, maybe not very high value as a product, but they can still be used as fuel or as feedstock to another process. The high cost of reactants often makes it essential to recycle streams, but recycle streams sometimes also recycle components other than reactants, for example, an impurity in the feed stream. Okay, and if you are recycling this impurity is going to build up in your system, and as such it is going to increase the volume of your equipment. It's going to increase your duty because you have higher flow due to this recycling impurity. So at some stage you have to take out of this impurity out of your system, and sometimes we use purge for this purpose. Okay, but the purge may well also contain valuable raw materials or products, so it means that you are also losing your product with the impurity in purge. Clearly there is a tension here and a trade-off between recycling impurities and losing the valuable material and producing waste streams that do have some value. Okay, and the final point is that sometimes in order to improve the performance of your reactor, we add dilutants or solvents or heat carriers, and these additional materials also need to be removed or recovered, possibly by recycling. So here we look at the idea of using a purge here. So a purge enables certain species to leave the process. In particular, for example, if you have an impurity and a byproduct or other materials that cannot leave the process in one of these separators, so in those cases, we actually use the idea of purge. So we remove certain part of your recycle stream, and as such, we take that impurity or byproduct out of the system. So the purge provides an exit point for these species. And normally the purge is just a simple fraction of the recycle stream. And the choice of purge fraction is an important one, and it's a degree of freedom in process design. As mentioned in the previous slide, that purge may contain valuable products, okay, and also some impurities. So a large fraction of purge would lead to a large flow of these valuable materials with the impurity as well. So you will be losing impurity, but you will also be losing a large fraction of your products or byproducts as well. But if you have a low purge fraction, then you are also recycling large quantities of these impurities back into the system. And as we discussed in the previous slide, that these impurities are going to affect the performance of your system and going to increase the heat duties and the size of your equipment. So again, we see this trade-off between recycling the material or losing the valuable material in this purge stream. And of course, it is logical to ask whether we can further process this purge stream. For example, we could carry out further reaction on this purge system to gain the valuable product species back from the purge stream, or we could carry out some separation on the purge stream and for the purpose of removing the valuable product back to the system. This slide reminds us that there are different flow sheet structures that can exist for a given input-output structure. And here we have figure A and figure B for this given reaction, that is A goes to B, B is our desired product, and then some part of this B can form a co-product, that is C. So if you look at this option here first, so here you have the feed and a recycled reactant, and then we fed that into our reactor, and then from the reactor, we in the first separation we have the separation of product B, and then the co-product, and the remaining unreacted A goes to the second separator, where we have the separation of C, and the unreacted A is recycled back to the feed. In option B, we have similar system, but here we have a different order of separation. In first separator, we are separating the reactant first. So reactant is recycled back to the feed, and then the mixture of product and co-product are fed to the second separator, and where we have the separation of product B and product C. In addition to these two options, we can also have a third option, where actually instead of having two separators, we can only use one separator. And here we are actually separating our product B, that is our desired product, and then we are recycling back our unreacted component A and our byproduct C, and some fraction of this stream is also purged out of the system. So we are removing C because we don't want to build C into the process. So what are the consequences of this flowsheet C? So one consequence is in terms of the capital cost, because we are only using one separator here. So obviously that is going to reduce our capital cost. But because we are recycling A and C both, so we are actually going to build more C in the system. So as such, we are going to have to increase our equipment size because we are now recycling extra product back. And that is obviously going to cost us in terms of the equipment size as well. Okay. So which of these flow sheets is the best will depend on its economic performance, as well as on its safety, environmental impact, and operability. The slide considers a different pair of reactions. A can react in two parallel reactions to either form B, that is our desired product, or it can form a byproduct C. And in this second reaction, this is also equilibrium limited, and this gives us a different flowsheet alternative where the unreacted A is recycled back and also the byproduct is recycled back to the feed. Okay, so now what would be the consequences of recycling C to the reactor? So in particular, the byproduct could react further, or it could have an adverse effect on the catalyst. Okay, so we have to think in terms of recycling C, how it can affect our reactor performance. In some cases, it could be possible to recycle all the C. In others, we would need an exit where we need to actually remove C from the system by using purge. And on the previous slides, we saw different separation sequences as well. So here we can also use different sequences. So instead of removing the byproduct in the second column, we can remove it in the first column, or we can instead of removing the feed and byproduct in the first column, we can actually recycle it from the second column. Okay, so again, the way we put the columns in a sequence can be different, and these gives us different options in terms of flow sheet structure. So this specific flow sheet structure, what we are trying to do is that we are trying to swamp the reactor with this byproduct C here, and which would actually drive the secondary reaction backwards because it's an equilibrium limited reaction, and by Legetrier's principle, we know that if we have a higher quantity of C, it will drive the reaction backward, and as such that would increase the selectivity of our desired product B. The last two slides considered flow sheets where the feed was pure, and it is unusual to have pure feed. Where there is an impurity in the feed, we need to understand how that impurity will leave the process. And here, for example, we have different flow sheets, and in flow sheet A, we have a separator that actually removes the impurity before the purified feed enters the reactor, where it is reacted, then in a separated and then recycled back to the feed. So this flow sheet would be a good idea if we have an impurity that is going to have an adverse effect on the catalyst in the reactor, and as such it will affect the performance of the reactor. So we want to remove this impurity before the feed enters the reactor. But if the impurity is in low concentration, so the separation may be quite difficult or it might be very expensive. Now, if we look at flow sheet B and flow sheet C, so here you can see that the impurity is removed from the system post reactor. Similarly, here you can see it's in after the reaction system and here as well. So which technology and where to remove impurity will depend on the properties of the reactant, the product, and the impurity. In flow sheet D, we have the impurity is being recycled but also purged at the same time. So in the purge, we are losing the impurity, but we are also losing our valuable reactants as well. As you can see here, there is one less separation unit in this flow sheet compared to the flow sheets in A, B, and C. So obviously, it is going to reduce the capital cost of the system, but recycling the impurity will increase its concentration. That is, it will decrease the concentration of the reactant and it will increase the flow rate of the recycle. And these changes will increase the size of the reactor that is needed to convert the same fraction of the feed. So it is not possible to say which of these is the best flow sheet without considering further details in terms of the operability, the economics of the system, and the environmental impact of these flow sheets. So that is all for this part. In next part, we will look at some heuristics which guide chemical process synthesis.